Good morning, students. We're back. Chemistry 411, Physical Chemistry 3, Module 4.1, Theories of Bonding. I hope you will enjoy the class. We're going to look at Introduction to Theories of Bonding, Molecular Orbitals, Hydrogen Molecular Ion, the Born-Oppenheimer Approximation, Linear Combination of Atomic Orbitals, and we make some conclusions. Introduction. The theories we're going to consider here are molecular orbital theory and valence bond theory. So basically there are two theories, the molecular orbital theory and the valence bond theory. Both theories are approximations. So these theories approximate how bonds are formed, that is formation of chemical bonds. They approach chemical bonding in different ways, but the results obtained are similar. We're going to see the valence bond theory assumes that each of the atoms retains its identity. On the other hand, the molecular orbital theory is an extension of atomic theory. So what we're trying to say is, in fact, it looks like, let me use two students who are roommates. In some situations, two roommates will be in a room. They are roommates, yes. But you find out that the two of them, they are using different foams. When you come into that room, you see two foams. If you look at the wardrobe, somebody's clothes is one side, the other one is the other side. They don't share clothes, nothing. Everybody is on his own, on her own. That is the valence bond theory. See where we say it assumes that each of the atom retains its identity. So the two roommates are sharing one room. They are roommates, yes, but they are not sharing anything together. When you still come to that room and look at individually, they still retain their individual identities. But on the other hand, using the same roommate analogy, you can have two roommates who come into a room. They are using one foam. They share their clothes. You don't even know who has what clothes. All they do is you wake up, pick up any clothes you want to use to go to school. They share so many things in common. Now, there are two individuals who have come together to produce another set of individual that is together. That's molecular orbital. And we're going to see that. So in this case now, we're saying that the molecular orbital is an extension of atomic theory. All the things that happen to atoms, we also treat molecules about the same way. So the only difference is that the atomic orbital is associated with only one nucleus, while the molecular orbital can be described in terms of more than one nucleus. Molecular orbitals. These are one electron wave functions obtained by solving the Schrödinger equation. Remember, we've met wave function before. We also met Schrödinger equation. And these are the descriptions for a molecular orbital. A molecular orbital, phi, that is a wave function, gives through the value phi squared the distribution of the electron in the molecule. So the same way we have distribution in atomic orbitals, we also have distribution in molecular orbitals, the electrons in molecular orbitals. Of course, we are going to see electronic configuration of molecular orbitals, just like we have electronic configuration in atomic orbitals. Molecular orbitals have the properties which are, similar to those of atomic orbitals. For instance, molecular orbital can be described by a wave function phi, which may cover the whole of the molecule. If phi is normalized through this equation, then phi star phi dt represents the probability of finding the electron in an elemental volume dt. Now, look at it. We defined an orbital as, a place where we have the highest probability of finding the electron. And now we're talking about the same orbital again in molecular orbitals. So we're talking about the greatest probability again in finding the electron in an elemental volume dt. The wave function may have quantum numbers associated with it. Again, we have quantum numbers with it, and shape and size of orbitals depend on their values. The same thing. That's why we said molecular orbitals are extension of the atomic theory. So we'll still have, quantum numbers associated with molecular orbitals, and shapes and sizes also depends on the values of these quantum numbers. There is a spin quantum number, ms, which has the same value of plus or minus half associated with each electron in the molecular orbital. In an analogous way to atoms, the electrons in the molecule can be fed into the calculated molecular orbitals in pairs, with ms plus half and the other with ms minus half, in order of increasing energy to give the ground state configuration of the molecule. So the same thing we're talking about in terms of atomic orbital electronic configuration. We're also saying that electrons can also be fed into the molecular orbitals that we obtain. We'll see how we obtain these molecular orbitals, and then still retain the spin quantum number plus half and minus half. Hydrogen molecular ion. We're now using the hydrogen molecule. This hydrogen is the simplest of the elements, and it's easy for us to use to make some of these predictions. The hydrogen molecular ion consists of 2 protons and 1 electron. Remember, it's an ion. If it is just hydrogen molecule, it will be 2 protons and 2 electrons. But for it to be an ion, it has lost 1 electron. So we're talking about He to power plus. That's H2 plus. Now this is hydrogen A, this is hydrogen B. At some point, if this electron is close to hydrogen A, then the molecular orbital will be described by phi 1sa. Remember that the electron is in 1s orbital, and this is A representing this atomic hydrogen A. Now it can also be closer to B, by which it will be represented by phi 1sb. Now look at the situation. These are the 2 roommates I described before. When B is the one supplying the money, which the 2 of them are eating, then B can take charge of the proceedings in the room. That's how it happens. When A is the one bringing money, A can take charge. Now these are the 2 situations, and when that happens, this will look like ordinary hydrogen. This will also look like ordinary hydrogen. And we're saying where A and B are protons, that is hydrogen atoms. In this case, the electron is under the influence of one of the protons. This will be more or less a hydrogen atom. You see what we're saying? And its property will be similar to that of an isolated hydrogen atom. So when it is here, it's behaving like just ordinary hydrogen atom. When it is here, it's also behaving like just ordinary isolated hydrogen atom. Now, if at any other time the electron is between these 2 nuclei, that is, it will be at the middle here. Now, assuming it is at the middle here, that is, we now have in between A and B, it is not going to be phi 1sa alone, it's not going to be phi 1sb alone. We can assume that the property is the sum of the properties of the 2 hydrogen atoms. Now, there's an approximation that helps us to do this. The Born-Oppenheimer approximation, and it supposes that the nuclei, being so much heavier than the electron, moves relatively slowly and may be treated as stationary as the electron moves around them. So now we are looking at this situation. As this electron is moving around this nuclei, this nucleus A and nucleus B is also moving, but their motion is very, very slow. They are moving slowly. So the Born-Oppenheimer approximation is now supposing that, let us assume that because this one is moving very slowly, we can assume that they are not moving, because their relative speed to this, if you compare it, this one is moving fast, very faster than this nuclei, because this nuclei is heavier than the electron. So we can now consider this and this as stationary and look at only the electron. We'll also explain the usefulness in some slides, in some lectures ahead, so that we understand this usefulness of the Born-Oppenheimer approximation. So using this Born-Oppenheimer approximation, therefore it is possible to choose the nuclei to have a definite separation R. So from here to here, is a definite separation, a distance of capital R. And then we solve the Schrödinger equation for the electron alone. And this is easier for us than solving the complete Schrödinger equation for this electron, for this nuclear, and also for this nuclear. Because if we do that, it will be very, very complex. So by this Born-Oppenheimer approximation, we can solve the Schrödinger equation for the electron alone. Now, the Born-Oppenheimer approximation reduces the full problem. You know, when we apply that, we are now looking at only one electron instead of two protons and an electron Schrödinger equation. So it reduces the full problem to a single particle Schrödinger equation for an electron in the field of two stationary protons at a separation R. Therefore, the potential energy of this electron is given by V equal to, remember our constant again, that is 1 over 4 pi epsilon 0. We've made this before. Minus E squared is because of charge of the electron and the proton. And now look at this. Arrow A is the distance from atom A. Arrow B is the distance from atom B when the electron is at the middle. The total energy of the molecule at the selected separation R is then the sum of the eigenvalues. Now these values, this a kind of iterated values, iteration values, eigenvalues and eigenfunctions, and the nucleus-nucleus repulsion. Remember, we have two nuclei. There will be repulsion between the two nuclei, and then this nucleus-nucleus repulsion energy is now equal to this. So we are now 1 over arrow A plus 1 over arrow B, which is halfway to B and halfway to A, will now give us a total sum of 1 over R, because this R is the separation between the two nuclei A and B. Now the Schrödinger equation for the electron in the molecule is then the same as that of an isolated hydrogen atom, and its lowest energy solution is an orbital on A, which is phi 1 Sa. Also close to B, the molecule resembles an atom and also have orbital of B, phi 1 Sb. Therefore, we now have a combination of this, phi equal to N into C1, phi 1 Sa plus C2, phi 1 Sb. N is a normalization constant. C1 and C2 are variation parameters. Assuming we're supposed to go into the advanced level, we'll start talking about variation parameters, but we'll still explain further in some slides where we now treat these variation parameters, their functions, and their usefulness. Linear combination of atomic orbitals. Now, what this means is simply the combination of atomic orbitals by simultaneous addition and subtraction. We are going to see the formation of these bonds. This wave function describes the electron in the molecule and its molecular orbital. We therefore form a molecular orbital by combining two atomic orbitals. Remember, the molecular orbital we're talking about, atom A of hydrogen and atom B of hydrogen, will give us a molecule of hydrogen ion. This method of forming molecular orbital is called linear combination of atomic orbitals. We cannot use any two atomic orbitals to get a molecular orbital. You must note this. It is not just any two orbitals that you can combine. There are conditions that will allow two orbitals to combine. So it's not just when you bring, maybe bring an s orbital and bring, py orbital, it will not be possible. So we have some conditions. To be able to obtain a molecular orbital, three conditions must be satisfied. You see what we're saying? The atomic orbitals must have similar energy values. The atomic orbitals must overlap as much as possible. The atomic orbitals must have the same symmetry properties with respect to certain symmetry elements of the molecule. So these three conditions must be satisfied before we can obtain a molecular orbital by combining two atomic orbitals. In other words, when we subject the two atomic orbitals under the same condition, if their behavior is similar, they can be combined. So remember, we're saying linear combination of atomic orbital is addition and subtraction simultaneously of atomic orbitals to obtain molecular orbitals. Now let's look at some examples of linear combination of atomic orbitals. Look at this. This s orbital is spherical. This another s orbital is spherical. When there is an overlap between s and s is this. So there's possibility for s and s to overlap. We also look at p orbital, p orbital. There's possibility for this overlap to take place. Of course, look at it. We will see later. This will be side. If it is side to side, it will give us a pi bond. If it is end to end, it will give us a sigma bond. Now, s and p orbital can also overlap, and we have this. Now, more examples of linear combination of atomic orbitals. Look at what we've been using as hydrogen. We now want to show the two constructive overlap and destructive overlap. This is addition. This is destructive. Look at the lobe. This is plus and minus. So eventually, what you have here, if you also say minus here, and you still have plus here and have plus here, but there's a minus here, is the same as this destructive overlap. That is negative. But plus plus here is constructive. And this gives us a sigma bond. Look at it. Together, you have formed a molecular orbital here. This is bonding. We are going to see that later. This is bonding molecular orbital. Now, but this, because this is positive, this is negative, they can't come together. So look at it. There is a line in between here. We'll call it nodal plane. That is a plane where we cannot find an electron. And this is sigma star. That is anti-bonding or anti-bonding. It's against bonding. Whereas this is bonding molecular orbital. You can see the difference. These ones cannot come close together. But this one has formed a complete molecule. We have used two atomic orbitals here, that is this and this, and we have obtained two molecular orbitals. One is bonding, one is anti-bonding. Thank you very much. We've come to the end of this module. We've looked at molecular orbitals, conditions for molecular orbitals. We've looked at hydrogen molecular ion. We looked at Born-Oppenheimer approximation and its usefulness to help us solve Schrödinger equation. We have also looked at linear combination of atomic orbitals. Of course, when we look at the structures of these homonuclear diatomic molecules, we will see the usefulness of this linear combination of atomic orbitals. I hope you have enjoyed this class. Thank you for listening and see you in the next class.